Hi, my name is Tatum Hardy. I'm an undergraduate aerospace engineering student at the Georgia Institute of Technology in AE 2610, and this is the combustion dynamics of a Rijke tube lab. The primary motivation of this lab was to characterize the chemical reaction rate of combustion within a Rijke tube by measuring the periodic fluctuating properties and acoustic oscillations within the Rijke tube. I'll begin by explaining the background of pulse combustors and the mechanics of the Rijke tube. Pulse combustors work by fluctuating heat release periodically, causing pressure and velocity oscillations. The strength of these oscillations grow until they are balanced by the acoustic losses in the combustor. A Rijke tube is shown and is a type of pulse combustor used in this lab. It's composed of a long vertical tube open on both ends with its heat source being a flame about 1/4 from the bottom of the tube. Pressure measurements are measured by piezoelectric transducers, which I've circled in yellow. When stress is on the transducer, a current is produced. The produced charge is measured and translated to a pressure measurement. These transducers are offset from the Rijke tube itself because they're sensitive to temperature and shock or vibration changes. I'll now break down the approach to the lab by explaining the instrumentation of the lab, the facility used, and the overall methodology of the lab. Georgia Tech's Engineering, Science, and Mechanics building was used to conduct the experiment because it houses a Rijke tube pulse combustor. The Rijke tube uses several instruments to model the system. The tools used in this experiment include a decoupler, which muffles the effect of an open-ended pipe, piezoelectric transducers, which detect combusting free radicals from the flame to characterize reaction rate by producing pressure-dependent current, the photomultiplier, which amplifies the effects of the detected wavelength so that it can be translated to voltage, the rotometer, which measures fuel flow rate, and an accompanying pressure gauge to measure flow, and finally, a data acquisition system or oscilloscope that interpret the received data from the transducers and photomultiplier to model the dynamical system. In our experiment, there are 3 different piezoelectric transducers at 3 different locations. These transducers detect pressure fluctuations at these points and translate these functions into voltage. The lab was conducted in 4 runs, each of which having slightly different Rijke tube environments. The first run had a flame at the 0-inch mark with the valve open. The second run had a flame at the 0-inch mark with the valve closed. The third run had a flame at the 2-inch mark with the valve closed, and the fourth run had this flame at the 6-inch mark with the valve closed. This 6-inch mark is where the pulsation cessation occurs. The total length of the Rijke tube is 72 inches, which will be more important for data reduction. The methodology of this lab can be broken into 2 parts: procedure methods and data reduction methods. The procedure methods are relatively simple and can be broken into 2 parts: ignite the burner in the Rijke tube and acquire the RMS voltages, peak frequencies, and associated phase angles for each of the flame locations and each of the sensors. In order to characterize the overall behavior of the system, 3 main values were reduced from the data: resonance frequency, amplitude, and relative phase angles. I've listed here the steps for calculating these, but we'll go into more depth in the following slides. We will now show an in-depth look at the data reduction and reveal results. First, the resonance frequency of the Rijke tube is calculated given the relationship between the length of the Rijke tube and the speed of sound at a given temperature. This temperature wasn't explicitly listed, so standard temperature pressure was used for calculations. As listed before, the length of the tube is 72 inches, and the specific heat constant in proper units is 286. When you put all these values together in the formula, you get that the resonance frequency of the tube is 94.44 Hz. The peak frequencies were as follows for the 4 runs for each of the pressure locations and the PMT. It's worth noting that the P1, P2, and P3 columns are identical. Notice that runs 2 and 3 produce the same results for the pressure transducers, and this value is close to resonance, which means that the tube resonates at these run configurations. Also, runs 1 and 4 are identical for the transducer values and are very far from the resonance frequency. In order to relate voltage to pressure, the calibration curve was used. Simply put, the slopes between the yellow circled points were calculated in average. This gave a relationship between PSI and millivolts. Since the RMS voltage was given in volts, volts had to be converted into millivolts in order to use this relationship. Once pressure was obtained, the sound pressure level conversion was performed to get the amplitude values for each run in decibels. The amplitude values were as follows. It's worth noting that runs 2 and 3 had relatively similar amplitude values, and runs 1 and 4 also had relatively similar amplitude values. This is to be expected given the relationship we outlined in the peak frequency slide. Finally, the standard deviations of each run show that there's not much variation in amplitude between the pressure transducer values. Finally, relative phase of the pressure was calculated by subtracting the associated phase of the chosen relative signal from the associated phase of the signal that was being characterized. Here, the middle transducer is the relative signal. The relative phase of the transducers in PMT are shown. It's worth noting that runs 2 and 3 are similar and almost exactly negative 180 degrees out of phase for P1, and runs 1 and 4 are similar and almost entirely in phase for P1. This would most likely be the case for P2 if P2 wasn't being used as the reference angle, given the recurring trends. Finally, an important relationship is showcased in the PMT frequency voltage table. It shows that as frequency decreases, so does voltage. This makes sense given that voltage is an interpretation of signal strength, and greater resonance corresponds to a stronger signal. A few supplemental questions are listed below and can be used to better understand the Rijke tube and the data. The answer to the first question is yes. Although this interference filter detects light with much longer wavelength than the light produced by the combustion of OH in the Rijke tube, which is what is being detected by the filter in our experiment to characterize reaction rate, other free radicals are produced by the flame in the Rijke tube that fall within this new wavelength range. Alternatively, if no reacting free radicals produce light in the filter's range, current would not be generated. If no current is generated, no useful measurements can be taken. The answer to number 2 is also yes. Hydrogen emissions produce light in the 415 nanometers to 450 nanometer range, which means that interference filter would detect the light and generate current that could be used to characterize the behavior of the dynamical system. Finally, the answer to number 3 is that if you want frequency to be variable over a small range, you'd need to change the resonant frequency value. This could be achieved by either changing the length of the Rijke tube or changing the temperature of the air. You could change the temperature of the air by allowing for variable amounts of fuel, which allows for variable amounts of combustion and therefore variation in temperature. This lab gave meaning to the word resonance. Resonance introduces disorder into the system. So in order to achieve the stability that we would like in the Rijke tube, pressure must drop. Another important conclusion is that closed-ended tubes result in more resonance due to greater wave reflection. All this being said, runs 1 and 4 are optimal for combustion because of their lack of resonance.